All right, let's dive right in. We're going to talk about the very bedrock of our universe. I mean, the three huge ideas that completely flipped our understanding of reality on its head. Yep, we're talking about the three pillars of modern physics.
But before we get into the nitty-gritty, let me ask you something. Something kind of big. The world around you, right now. The chair you're sitting in, the air you're breathing. Does it all seem solid, predictable? Well, what if I told you it's not? As we're about to find out, the answer is a big, resounding nope.
You know, for hundreds of years, we thought we had it all figured out. Reality seemed, well, simple, intuitive, kind of like a giant machine. And the guy who wrote the instruction manual for that machine was Isaac Newton, way back in 1687. We call it the common sense universe. Everything just ticked along like a perfectly wound clock.
Okay, to really get this, picture two marbles, just two simple marbles. In Newton's world, what do? Well, they travel in straight lines at a constant speed, super simple, super predictable. They're just separate little things doing their own thing. Now, I want you to hang on to that image of those two marbles, because their story is about to get really, really weird. So everything's chugging along just fine, and then we hit the 20th century. And scientists start doing these new experiments, and they start seeing cracks in that perfect clockwork model. It turns out reality was, well, a whole lot weirder than Newton or anyone else could have possibly imagined. And that's what led to this huge revolution in science, built on what we now call the three pillars.
All right, pillar number 1, universal gravitation. And this one is a doozy. It completely shatters an idea we all take for granted every single day, the idea that things are actually separate from each other.
So here's the mind-blowing part. Every single particle in the universe is pulling on every other particle. Yeah, you heard me. The pull gets weaker the farther away you go. Sure, that's the inverse square law, but it never ever goes to zero. It's not just the Earth pulling you down. You, right now, are pulling on the Earth. You're pulling on the sun. You're pulling on a star in a galaxy billions of light years away. It's like this invisible web that connects, well, everything.
Now, how strong is this pull? Well, it's all governed by this one special number, the gravitational constant, which we just call G. And just look at that number. All those zeros, it's ridiculously tiny. What that's telling us is that on the scale of our everyday lives, gravity is actually an incredibly weak force, like unbelievably weak.
Let me give you a way to picture just how weak it is. Imagine two cars, not little ones, like one-ton pickup trucks. And they're floating out in deep space, maybe just a yard apart from each other. Even with all that mass, that much metal, their gravitational attraction is so feeble, it would take them hours to slowly drift together and finally touch. That's how weak it is.
So think about that. This force is so weak, but it's also strong enough to hold entire galaxies together. It runs the whole cosmos. The fact that this universal web of connection even works at all, well, that just shows us how weird our universe really is.
But, okay, gravity wasn't the only thing shaking up the old Newtonian world. Fast forward to 1905, a guy named Albert Einstein comes along and gives us pillar number 2, special relativity. And if gravity shattered the illusion of separation, this one shatters the illusion of absolutes. The idea that time ticks the same for everyone and a meter is always a meter, yeah, about that.
The core idea here is, it's a real mind-bender, so stick with me. It's this. No matter how fast you're going, no matter what direction you're heading in, if you measure the speed of light, you will always get the exact same number. Always. Now, for that to be true, something else has to give. And that something else is, well, space and time. They become flexible, stretchy. They warp themselves just to keep the speed of light constant.
And the results of this are straight out of science fiction. I mean, for real. The faster you move, the slower your clock ticks compared to everyone else. The faster you move, the shorter you get in the direction of motion. And get this, two things happening at the same time isn't even a real thing anymore. It depends on who's looking. It all comes down to one cosmic speed limit. Nothing moves faster than light. And this isn't just some crazy theory, by the way. The GPS on your phone, it has to do these exact calculations every second, or would be off by miles every single day.
The magic number here is c, the speed of light. And unlike g for gravity, which was tiny, c is just mind-bogglingly huge. We're talking almost 300 million meters every single second. And that's the reason we don't notice time slowing down when we're in a car. You have to get going unbelievably fast to see these effects.
Want to feel for that speed?
Think about your internet. The light zipping through just 1 foot of fiber optic cable, that takes 1 nanosecond. 1/1000th of a second. That's how fast we're talking, and that's the absolute, unbreakable speed limit of the universe.
So what does this mean? It means time isn't universal. A meter isn't always a meter. It all depends on how you're moving. Your reality is personal to you. The fact that we live in this kind of stretchy, rubbery version of space-time, well, that just shows us, again, how weird our universe really is.
Okay, so we've got a connected universe and a stretchy universe. But if you think it can't get any stranger, just you wait. Here comes the third and final pillar, quantum mechanics. And this one goes after our most cherished belief of all, the idea that reality is certain, that it's predictable.
Let's try to wrap our heads around this. Our common sense tells us, right, that an object is in a specific place. A particle is a thing, and a wave is a wave. They're different. But the quantum view? No. It says a particle is also a wave, and a wave is also a particle. They're the same thing. An object, like an electron, doesn't even have a definite position. It exists as a cloud, a wave of possibilities, until the moment you look at it.
And the number that runs this whole bizarre show is called Planck's constant, or h. And just like the gravity constant, it is impossibly small. Just look at it. And that tiny value is why we don't see this weirdness every day. It's why a baseball doesn't act like a fuzzy cloud of probability. All this quantum uncertainty is kind of locked away down in the tiny, tiny subatomic world.
But make no mistake, that uncertainty is real. It's always there. For example, a teeny tiny grain of dust sitting on your desk. Quantum mechanics says there's a chance it could just move spontaneously by about 1/1000th of an inch. Now the catch is, you'd probably have to stare at it for about 30 years for it to happen. So the effect is real, it's just really, really subtle when things get big.
So what does this mean? It means the universe, at its very core, isn't a nice, predictable machine. It's a casino. It's all about probability and chance. The solid world that you see around you is built on a foundation of, well, ghosts, a shimmering sea of uncertainty. And the fact that this works at all, that it builds our reality, well, it just shows us how weird our universe really is.
So, where are we now? We've torn down our old ideas. Separation? Gone. Absolutes? Gone. Certainty? Definitely gone. What we're left with is a completely new picture of reality.
If you take away one thing, let it be this. Pillar 1, gravitation. Everything is connected. That shattered the illusion of separation. Pillar 2, relativity. Space and time are flexible. That shattered the illusion of absolutes. And Pillar 3, quantum mechanics. Reality is just a game of probabilities, and that shattered the illusion of certainty. These are the new rules. This is how the universe actually works.
Okay, let's go all the way back to the beginning. Remember those 2 simple marbles? Let's look at them again, with our new eyes. First off, they're not separate at all, are they? They're forever linked, weakly pulling on each other across the entire universe. Second, they don't experience the same time. Each marble has its own personal clock, ticking at a rate set by its speed. And third, they don't even have a real position, not until you look. Until then, each one is just a fuzzy cloud of pure possibility.
So, that simple, common-sense, clockwork universe we started with, it's not just a little bit off, it is completely, fundamentally wrong. The reality we're actually living in is, well, it's more connected, more flexible, and way more mysterious than our brains are really built to understand.
And honestly, that's what makes it so amazing. The fundamental rules of everything, from a single atom to an entire galaxy, they're not just weirder than we imagine, they might be weirder than we can imagine. Our universe isn't just strange, it's stranger than any story we could ever write.